Good morning everyone. Yesterday we have already discussed about the vapor pressure of liquid solution and Raoult's law. Complete derivation we have solved already. Okay. So today we will take a new topic, that is mole fraction in the vapor phase. As I already told to you, whenever you are talking about the gaseous phase or vapor phase, you have to apply the Dalton law. Okay. And Dalton law, it is applicable for gas in gas. Okay. It is applicable for gas in gas. Okay. Now you can tell easily that Raoult's law is applicable for liquid in liquid. Okay, we have discussed Raoult's law applicable for liquid in liquid, and Dalton law it is applicable for gas in gas. Okay, so now you can see here, according to Dalton law, partial pressure of each component, whatever component you are taking here, suppose A component you are taking here, is equal to mole fraction in gaseous state of that component multiply with total pressure. Okay, this term you have to use for the Dalton law. We have done this topic in 11th class. Okay, so derivation we have done in 11th already. So we have to use this formula. P total means if two component you have taken, and total pressure that must be applied by that component is equal to total pressure. Okay, so that only we have written here. But whenever you are using the mole fraction in vapor phase, our representation will become in terms of y. In liquid phase, we are using x. So same thing written here. For one component, partial pressure is equal to y1 p total. For component 2, partial pressure of two component is equal to y2 is equal to p total. Now our next topic is vapor pressure of the solution of solid in liquid. Okay, so Raoult's law we have done derivation for liquid in liquid. Now we will do Raoult's law for solid in liquid. Okay, if you are taking solid as a component, earlier we have taken liquid in liquid, liquid we have taken, definitely that was the volatile, but here we are taking the solids. So solids if you are taking, it must be a non-volatile. Okay, so we all know very well solid do not exert any vapor pressure. That's why it behaves as a non-volatile. So we can easily learn this, that what is the meaning of non-volatile? Which do not exert any vapor pressure, but volatile which can exert pressure. So we are using here solids, it means it act as a non-volatile solute. So you can see the derivation. If you want to calculate the total pressure, then it must be equal to partial pressure of A plus partial pressure of B. Okay, but if you have taken this partial pressure of A solute as a non-volatile, if it is non-volatile, it will not exert pressure, then its value will be 0, plus PB is equal to P total. Now total pressure exerted by the mixture, that is only because of pressure exerted by B. Why it is not because of A? Because it is non-volatile. Okay, so we have to consider only the one component in a mixture to get the total pressure. So total pressure we can represent in terms of P solution also. Like this also we can write, and it is equal to PB. Okay, PB, whatever you can consider it, here you can consider solvent. Okay, so we can write like this, P solution is equal to P solvent. Okay, P solution is equal to P solvent. So as we know already, P solution is equal to P solvent. P solvent means pressure, partial pressure that is exerted by the solvent, and that is equal to P naught into X solvent. Okay, in terms of solvent only we will take here. If you want to write in terms of number, you can write here X1. P naught is equal to P solution. One, it is used for the representation of solvent. And what is P naught here? It is the vapor pressure that is exerted by the pure solvent. Okay. So you can continue this derivation. Partial pressure of any one component is directly proportional to mole fraction of that component. I have already told to you P total is equal to P1 plus P2. Okay, P1 is equal to X1 P1 node and P2 is equal to X2 P node 2. But here we have considered that one component is non-volatile. That's why I have taken this value equal to 0. Okay, now P total is equal to only and only because of solvent. Okay, only and only because of solvent. So here solution will not come. It is only because of solvent. Okay, so now you can write here P total is equal to P solution. Here what I have written here, because P total it is because of both component, but we are getting only because of solvent. So P total we can write here P solution also. Okay, but it is only because of what? P solvent. So you can see here, if you can keep this P node 1 down of this, then this formula will become equal to this one. Okay, P solution divided by P node 1 is equal to X1. Okay, if you will subtract this both terms from 1 minus this one, P solution by P1 is equal to 1 minus X1. So we can put 1 minus X1 is equal to X2. We know already that X1 plus X2 is equal to 1. So we can write here 1 minus X1 is equal to X2. Okay, and this is the mole fraction of solute. So we can write, if you want to write the mole fraction in terms of solute, you can put the 1 minus X1 is equal to X2 and take the LCM of this. Okay, so you will get the complete formula P node 1 minus P solution divided by P node 1. Okay, now you can see P node minus P solution. P node 1, it is the vapor pressure that is exerted by the pure component. Pure component means suppose you have taken the water. There is no solute present, then it will exert maximum pressure. Maximum pressure means whatever the total pressure exerted by it, it is only because of water only, because it is pure. So it will exert more pressure as compared to P solution. Why? Because in P solution, two things present, solute as well as solvent. Okay, and solute will not allow the solution to evaporate. Okay, that's why the vapor pressure because of solution it will decrease. It will cover the surface of the solvent. So we can say that P node minus P solution, because of this term some vapor pressure will decrease. Okay, that's why we can say it is called lowering in vapor pressure. Okay, P node suppose it is 100 and P solution it is suppose 40. Okay, then 100 minus 40 it will be equal to lowering in vapor pressure. But if you are using this complete formula P node minus P solution by P node, then it is called relative lowering in vapor pressure. Why it is called relative lowering in vapor pressure? Upper one you are saying it is lowering in vapor pressure, but you can compare it with pure solvent only. If you are comparing it, then you will use the term relative. P node minus Ps divided by P node 1, then it is called relative lowering in vapor pressure. Okay, and this final derivation, this final formula we have done, it means this RLVP, relative lowering in vapor pressure, is always equal to mole fraction of solute. This term, this formula you will use in numerical. But you can see here, there is a graph for that. We have done for liquid in liquid. Okay, graph for liquid in liquid we have done like that. Here you will take x1 is equal to 1, x2 is equal to 0. Here you will take x1 is equal to 0 and x2 is equal to 1. On this line only and only which component present? X1. On this line only and only which component present? X2. Okay, so like this graph we have done already in Raoult's law. Okay, this gives the total pressure and this will give the partial pressure of each component according to their presence. Okay, so now we are doing Raoult's law for non-volatile solute, in which one component is solid. Okay, if one component is solid, then it will not exert any pressure. That's why you have to remove one line from there. Okay, I have removed this one line, then you will get this graph. Okay, why? Because you are having only one component, that is solvent, which will exert the pressure. Okay, so here if one component is present, okay, one component is present but it is non-volatile, then you will not show any graph for that. Here component 2 is present and it is a solvent, it will exert the pressure, then you will show the graph for that. So single line you will get only here, and at this point you will get the vapor pressure of the pure solvent. So finally you can see here few important terms I am telling to you that you should know. Dalton law, it is applicable for gas in gas. Clear? Henry law, it is applicable for gas in liquid. Third, Raoult's law, it is applicable for liquid in liquid if it is volatile. Second part, solid in liquid if it is non-volatile. Okay, in 1 marks question they are asking Dalton law, Henry law and Raoult's law. So Henry law we will discuss later on. So our next topic is ideal solution and non-ideal solution. Okay, we have done Raoult's law. So what is ideal solution? It is the solution which can obey Raoult's law. It will obey Raoult's law under all condition of temperature and concentration. Whatever the temperature or concentration you are taking, if it will follow the Raoult's law, then it is called ideal solution. Okay, so according to Raoult's law, what is the partial pressure? Partial pressure of any component is equal to vapor pressure in pure state multiply with mole fraction of that component in of that component. Okay, this is the Raoult's law. If it will follow, then it will be equal to this. Okay, it means this multiplication must be equal to the partial pressure of that component. But in ideal solution, because it is following the Raoult's law, after mixing two component you have taken 1 and 2, after mixing you will not get any change in enthalpy. Okay, why? If you will add the two components, the change in energy that was before the mixture is equal to after that combination also. Okay, so definitely we can say del H must be equal to 0 because there is no change in enthalpy even after mixing. So we can write now del H mixing is equal to 0 because there is no change. In the same way you can say delta V change in volume is also equal to 0. If you will take two component 1 and 2, first one having a 1 liter volume, suppose second one is having a 2 liter volume, then after mixing definitely you will get the 3 liter only. But if you will say that we are getting definitely after addition the same volume after addition, so it is not possible in all cases because we are not taking here the normal daily life substance, we are taking here the chemical compound. Some chemical compounds are reacting also, that's why it will decrease the volume as well as it will increase the volume. So we are talking about here reactions. Okay, we are not taking a daily use substance. So three things you must know: del H, del V, it is equal to 0. If it is following the Raoult's law, P1 is equal to P1 naught x1. Okay, so now again one more thing, the reason behind that they can ask from you why volume will not change, because there is no reaction between the two component A and B. There is no reaction between the component A and B. Why? AA molecule I have taken, okay, A2, and BB molecules I have taken. The forces between AA and B, it is almost nearly equal to each other. Okay, that's why after reaction also it will shows the same effect. Okay, the forces of interaction between the both the component, it is equal. Even after reaction it will become definitely the same. Then volume will not change. If volume will not change, then del V will remain same. Okay, del V is equal to 0. Okay, in forces of interaction, if it is same, then definitely energy change will not occur. If energy change will not occur, then del H will be equal to 0. So example you have to learn, very important example, benzene and toluene. Okay, hexane and heptane. You can see here in ideal solution similar compound we are taking. What is the chemical formula of benzene? It is this one, and of toluene, benzene with CH3. Only one carbon difference it is there. Okay, so similar, nearly equal molecular weight we are taking in an ideal solution. In N-hexane or N-heptane, in the same way, only one carbon difference it is there. So now you can see the next term, known ideal solution. Definitely it will be the opposite to that of ideal solution. In ideal solution we have done, it will obey the Raoult's law. Okay, but it will not obey ideal, non-ideal solution will not obey the Raoult's law. It shows some deviation from the Raoult's concentration and temperature. Is that clear to all? Okay, and this is called non-ideal solution. So one thing you should know, suppose you have taken a solute BB and solvent AA, okay, AA, and you have added with BB. After mixing, if forces of interaction will increase, then you will say na, forces of interaction will increase, then they will come close to each other, they will make a strong bond. If they will make a strong bond, then it is difficult to evaporate. Is it clear what I said? If AA and BB component you have taken, after mixing, forces of interaction increases, then strong bond will be formed. Strong bond will be formed. Definitely it is difficult to evaporate. If it is difficult to evaporate, volume will not increase. If volume will not increase, then change in del V, it will becomes negative. Okay, it will become negative. In the same way, if you have taken the component AA and BB, after mixing, AA and BB, after mixing, if the forces of interaction decreases, if forces of interaction decreases, the bond formed will be weak, and bond formed will be weak, then it definitely it will evaporate easily. If it will evaporate easily, then volume will increase. Okay, then result will be positive. Okay, so on the basis of that, we have divided non-ideal solution into two parts, into two types. One is positive deviation, other is negative deviation. Okay, so first we have taken positive deviation. In positive deviation, total volume will increase, total change in enthalpy will increase. You can learn, if it is positive, definitely value will be positive. Okay, so why it is positive? Volume, when volume will increase, if escaping tendency will increase. If escaping tendency will increase, then forces of interaction will be less. Okay, then partial pressure also it will increase. So same graph you will use here, we have done in Raoult's law for liquid and liquid, same graph. Okay, but some deviation how you will show, because everything it is increasing here, then partial pressure of A component will increase, partial component of B will increase, then definitely total pressure will also increase. Okay, so everything same we have taken here, mole fraction, this is the vapor pressure. So our next type, it is negative deviation. Okay, negative deviation, in that everything will be negative, del H will be less than 0, del V less than 0. It means total volume will decrease and total change in energy will also decrease. And why energy will decrease? Negative will, it is coming, na, volume will decrease. Why volume will decrease? Volume will decrease if there will be a strong forces of attraction. Strong forces of attraction, then strong bond will form. Strong bond will form, then it will not evaporate. If it will not evaporate, then volume will decrease. Definitely the partial pressure will also decrease. So 3 difference you have done here, okay. And example, it is very important. This is the example of positive deviation, ethanol with acetone or carbon disulfide with acetone. Okay, acetone you can learn. Acetone we are using as a nail paint remover also. If you will use acetone nail paint, it will remove by using a trick you can learn. Means in positive deviation acetone and ethanol will come, okay, and acetone carbon disulfide will come. In negative deviation you will look here, phenol and aniline, chloroform and acetone. So at least one example you should know of each. Ideal, non-ideal. In non-ideals it is of 2 types, okay. So you have to do up to this. In next lecture we will start the topic azeotrophs. So thank you and have a nice day.